This is a continuous spectrum where all frequencies are present. This is a disc lines. Amplitudes of those spectral lines will distribute according to the sinc shape. One more question. Hope this explanation is okay now, right? Before I move on. Single pulse spectrum and repeated pulse spectrum. The difference is that single pulse spectrum will be continuous spectrum. All frequencies will be present, but spectrally distributed according to the sinc. Repeated pulse, which is called the pulse train, will have a discontinuous spectrum where only spectral lines are present. Amplitude of spectral lines will distribute according to the sinc shape. So remember that summary, right? Then one more question. So pulse train is unlimited in time and sinc is also unlimited in frequency. So how is it possible to have unlimited duration in time and frequency? Pulse is, you mean this pulse, right? This pulse is time limited and its sinc shape unlimited number. But here time unlimited, frequencies are limited here. You only have spectral lines. You don't have unlimited number of frequencies. So that is what I just explained. Frequencies will be limited now with gaps, integer gaps of fs. In between frequencies are absent here. So that means all frequencies are not present, right? Hope it is clear now. Okay, so with that summary, let us move on to apply this idea back again to our previous analysis and see what are we trying to understand here. So earlier we analyzed impulse sampling, assuming impulses, but now no impulses, all are pulses, having a pulse train given by this space, this equation. So we should be able to substitute this in place of the impulse train in our earlier analysis. Let us do that now. Here we are doing a pulse modulation. Actually, we are modulating amplitudes, right? Which I already explained. We are varying the amplitude of the practical pulses having a pulse width tau according to the instantaneous voltage variations of our information signal. Mathematically, it will be like this now. Sorry, graphically, it will be like this. Pulses have a practical tau value and their amplitudes are being modulated, being varied according to instantaneous variations of modulating signal voltage. Now, we can have two options here. One option called natural sampling, another one called flat top sampling. What is meant by natural sampling is that top of each sample does not remain constant and they just follow the xt variation. It's like this. If you take xt like this, and if you take a sample like this with a finite tau value, pulse width is there, top of the sample will be just following this variation xt. So it's not a constant. That's called natural sampling. But if this top of the sample is made flat like this by clipping off this section, then it's called flat top sampling. So two options are there. Natural and the flat top. Natural sampling is very simple. You just allow xt to pass through a analog gate like this, which will be switched on and off according to your pulses. And there are FETs which can do this at high sampling rates. Then resulting XST will be having natural variations in the top of the sample. It is not flat. Right? It will just follow XT like this. So natural sampling. Analysis, we can just repeat what we did for the impulse sampling. Now our PT, this one, we know it's not impulses now. Its frequency domain, its time domain will be this one, which we already proved, right? PF also we already proved. It is that sync shape spectral lines having sync amplitude variations. These two we have already proved, right? They both relate to this pulse train PT. Now, it's a multiplication, isn't it? XST is the multiplication of PT and XT. If you take time domain XT, time domain PT, and multiply the two, your pulse amplitudes will be modulated. So just multiplication in the time domain, which means we can take the convolution in the frequency domain. So XSF will be the convolution of XF and PF. Both we already know PF is this. XF could be that our modulating signal, whatever the shape it is, just convolve the two. Let us take this example and substitute import PF here. So XF will become convolution of XF and this, which means spectral shape of XF will repeatedly appear at every intervals of every spacing of Fs there, like this. So we can just say F minus Fs, and you can notice it repeatedly appearing at every Fs. Sampling theorem is still holding here. So you have to do this according to the sampling theorem, otherwise you can't recover this original. However, what is the difference between this and the previous impulse sampling? Difference is this portion. Earlier this amplitude was flat, but now it is a sync. So what will be the impact then? Impact is that because of the sync shape here, high frequency content of your original signal will be attenuated according to the sync shape of the top of the pulses here, top of the spectrum here. So that has to be corrected by using a filter, which we call an equalizing filter. So that is the impact when we have practical pulses instead of impulses. Right? Because the amplitudes are getting affected, they must be corrected again. Let's have a break, and after the break, we will discuss how this equalization can be done. Right? Shall we meet after 10 minutes from now?
Recording stopped.
Okay, we will resume. So we noticed that when we use natural tops in the samples, our spectrum of the sample signal will have an extra amplitude variation given by this sink shape here. So we need a filter which is reciprocal of this shape. 1 over sink NFS tau. That kind of amplitude variation we need to introduce in order to correct this issue. Okay, how do we do that? Before moving to that point, shall I introduce flat top sampling also here because we were comparing the two. And as you can see on the screen, the second graph is having flat tops here in every sample. So it's obvious, I think, samples are now not following the natural variation of xt. Instead, it's like an impulse at initial moment to take the sample, and then that sample amplitude is held constant. Sample amplitude is held constant over the period tau. Right? And this is a typical sample and hold circuit. They are called SNH, sample and hold circuits. There are ICs like, for example, LF398, which perform this function, sample and hold function. Right? The idea is like that you have xt here at the input, variations are there. Then you switch on this analog gate to allow a sample of that amplitude be taken into this capacitor. So capacitor voltage will represent the sample. There will be a small time needed in order to charge the capacitor, which we call the aperture time for charging. And then, sorry, it's called the sampling time, the time to take the sample. And then you shut this gate, disconnect the input from the capacitor. Capacitor is the voltage is now available to the output. Right? And to minimize the current effect of the current drawn, you may use operational amplifier buffer circuit here to take the output. You can put a buffer circuit here also at the input to buffer the input side as well. So normally those sampling and hold ICs have input buffers and output buffers, which are not shown in the figure I have drawn here. But be aware, right? Two buffer circuits are there on either side. And after you have taken the sample, you close this gate, disconnect the input, and you hold the capacitor up to the required time tau. And at the end of the tau, you will switch on this gate so that the capacitor will be fully discharged back to zero, and that will be this time period. You keep this gate G2 on over this period, and after that you open the G2 gate, close the G1 gate to take the next sample. So G1 and G2 gates are pulsed accordingly, and they are never switched at the same time. Right? Never switched at the same time, because in that case you will be short circuiting the input. So they are switched on and off with proper timing to take the sample and hold. Right? Holding time is controlled by G2, and moment at which you do the sampling is controlled by gate G1. There are JFET or MOSFET switches with low channel resistances which can do this switching action. So both G1 and G2 will be such transistors. And input and output buffers I already mentioned, because you need to isolate the two sides properly and provide proper impedance matching with enough current drive capability. That's why op-amp buffers are required at the input and output when you make an IC. Today, most of the analog to digital converter ICs already have the sample and circuit integrated into it. If not, you have to connect it from outside. I already mentioned about the acquisition time, which is the time taken for the capacitor to reach its correct value. Time taken for the holding capacitor to reach the correct voltage value. That will be a small time, charging time. And this is aperture time is the time over which you hold it. So your amplitude will rise like this. If I exaggerate it, it will rise and then held. Sorry. This is highly exaggerated when I drew. This is the aperture time, sorry, acquisition time. And aperture time is the time you use for holding. But acquisition time is made low, so that overall tau will be the summation of acquisition time and aperture time. They are in the specification of the IC. So when you read, now you know, right? What are these times? When you read the IC data, these times are given by the manufacturer. Right, let's look at it mathematically. Each pulse is given like this, a rectangular pulse with the width of tau, and assume that you take an impulse train. Assume that you take a train of impulses like this. Sorry, with constant amplitude, I'm sorry. Train of impulses with constant amplitudes. And you do convolution between that and this pulse, PT. This pulse PT and the impulse train, when you convolve, pulse PT will recur at every interval like this, with the amplitudes being different according to the variation of xt. So the convolution will result this flat top sampled waveform. Therefore, we can write XST as the convolution between individual pulse PT. This is not the pulse train, this is PT pulse, and the impulse train. So XST could be written like this. And the convolution in the time domain can become multiplication in the frequency domain. So if I want XSF, I can multiply PF with XF. Both PF and XF are known to us, so we'll directly multiply to see the spectrum of the flat top sampled waveform. Just multiply the two. We get that one, right? PF, I'm substituting from our earlier derivation of spectrum of the single pulse. Right. So what does this mean when you plot it? Again, you have on the frequency axis, spacing is integer multiples of fs, and this sinc shape is repeating. So we get almost the same, shape of the spectrum as what we got for the natural sampling. Right? Then when you reconstruct this or interpolate this, what will happen? Let's consider mathematically again, x is in time domain, frequency domain, both are known to us now. In the frequency domain, it was like this. Our issue was that this shape was not flat here. Shape was sinc, and that problem is there whether we use flat top sampling or natural sampling. Both cases, it was this sinc shape present, attenuating the higher frequencies of the information signal. So XST, you need to pass through equalizing filter, also known as interpolation filter, another name, which will correct this shape here. And then you can get the original. This filter should have a response which will have cutoff in these places. Cutoff is like this, but it is not perfectly rectangular. Why? This portion need to be corrected. Therefore, the top will be inverse of this one. Top will be the inverse of this, like this. Should be 1 over or reciprocal of this function sinc. So we need a filter of this shape when we are using practical pulses instead of impulses. Right? Impulses needed a flat top there, but here it is an equalizing top where higher frequencies will have to be boosted by a little amount according to this reciprocal of sinc function. Then original can be obtained here. Okay, so because it is 1 over PF, your equalizing filters transfer function should be 1 over PF. This TS is because you have FS here. Right? To correct that, you anyway needed TS. Remember, in the impulse situation also you needed TS. So this was there anyway. And now that divided by PF will be there, which is reciprocal of sinc shape here. So for frequencies less than B, it will be the reciprocal of sinc. Frequencies higher than B, it should be 0. This is the transfer function of the interpolation or the equalizing filter. Now in time domain, reconstruction in frequency domain is what I just explained. Okay, this it's SF multiplied by equalizing filter response will recreate XF. In time domain, this one convolve with impulse response, which is the Fourier transform of this function EF, will recreate the original waveform XT. Okay. Time domain convolution, we'll look at more closely here now. Supposing we are retrieving the values of amplitude data from incoming channel, or it could be recovered from a storage, stored amplitudes. and we are convolving them with PT, then passing through an equalizing filter with a response that is proportional to the inverse of PF, and that will recover the original XT. So this is what we mathematically do. Take the amplitude values from the incoming channel or from a storage, multiply by PT, and not multiply, convolve, and then put the equalizer. Here, before the equalizer, it will be the original PAM signal given by that. And also these pulses are actually the pulses we assumed as centered, but here you can see they are not centered. Amplitudes are taken with the offset like this, 0.5 to offset, which we did not accommodate. So we can apply that 0.5 to offset to PT as well, this way. I will use a non-ideal PT, which is having the offset now. What do you mean by offset? This amount. So it's a rectangle with the pulse width of tau, but offset of 0.5 tau. And now it's having this offset correctly set. When you have the offset, your frequency domain will have some e to the power value, e to the power component coming like this, right? E to the power minus j phi ft will come due to this offset. That comes due to that. And rest is same as earlier, right? So basically, now you know how to derive the equalizing filter function, right? Sorry, how to derive EF as a reciprocal of the frequency response of frequency spectrum of the pulse train. Okay, so we know our PF. Then substitute that here. Then you can calculate your EF function. This whole thing is EF. And that EF is the response of this equalizing filter. So that's how we mathematically reconstruct or interpolate the in-between values of the original waveform. One special case of this flat top sampling is called staircase sampling. It is flat top sampling itself, but your pulse width is same as now sampling time. So your pulses will occupy the total sampling time like this, creating a staircase look. So therefore your tau will be same as TS. But that is a special case only. It's same kind of interpolation happens. Name given for this in theory is called zero order hold. Zero order hold. That will generate the staircase. Then between samples, you can use linear interpolation also if you want. Rather than ideal one, between samples, you can fill them linearly. In that case, it is called the first order hold, right? First order hold. And that mathematically, instead of the rectangular shape, if you use the triangular pulse mathematically, it is called the first order hold scenario. And so likewise, there are variations possible. Okay, I think now we have discussed how to handle non-ideal pulses. No, so impulses are not there. We had to use flat top or natural tops. And now we know how to make the adjustments in our equalizing filter to correct the amplitude issue. Then practically, the sampling is a very common function between the analog and discrete worlds. When you consider audio, typically commercial telephony sample your audio waveform at 8,000 samples every second, and it has become a standard, and they use 8-bit word lengths for commercial telephony. But this is not good quality for music or high fidelity applications. And there are systems which sample at 32 kilohertz for better quality, especially for good quality audio transmission requirements. You use 32 kilohertz sampling. Even for recording, right? When you record also, you can choose your sampling rate depending on the quality you want. And the CDs and other similar consumer devices, they use 16-bit word lengths, and they sample at 44.1 kilohertz standard frequency. And that way they can have much better quality for audio, which has even 96 decibel dynamic range in their variation of amplitudes. Then for even better quality, you can use 96 kilohertz sampling, very high quality studio recordings. And they typically use 24-bit word lengths, and they can handle audio with 144 dB dynamic range. You can now see the quality can be traded off with the bandwidth. Video at is a standard sampling rate, 13.5 megahertz for luminance signal or the brightness signal with 8-bit samples, but the chrominance signal, which is R minus Y and B minus Y, red minus yellow, and blue minus yellow, then those chrominance signals or chroma signals are sampled at 6.25 megahertz. These are standard values, right? So better to have an idea about these industry standards when dealing with audio and video in the digital domain. Now that we know how to do the sampling, after we have done the sampling, our amplitudes could be any value, right? But in digital domain, we can't have any value. We have to have some discrete quantized levels. And that step of approximating sample amplitudes to nearest quantum levels, quantization levels, we call quantization. Let's look at that now. What is quantization? Earlier, after pulse amplitude modulation or after sampling, we just got amplitudes of different values. Let me give you a set of values as examples. Assume that we took PAM, and after we quantize, we should have the amplitudes approximated to standard quantized values, quantum values, we call them. An example will make it clear. Assume this is our PAM signal. We have not quantized yet. We have just sampled amplitudes of each sample represented by, say, this many millivolts, right? I'll assume these amplitudes are in units like millivolt. So first one has 24, 38, likewise. So these could represent individual amplitudes. However, we can't have all values transmitted in digital. Therefore, we need to approximate them to nearest standard values or quantized values. So the quantization is the process of actually approximation. You segment a sample signal into certain discrete voltage levels where each level will correspond to a different binary number later. So this approximation process will create errors. whenever amplitudes are approximated to the nearest quantum value, there will be an error in the amplitude. That is irrecoverable. You can't recover. But in the sampling, you could recover everything. Original could be recovered. But when you quantize, that damage you create due to quantization is irrecoverable. It will remain. Therefore, you got to be very careful here in selecting how many quantized levels you use. More levels will be better. But more levels means you need more bits per sample and you need higher bandwidth in your signal. Again, a compromise is what we are looking for. Okay? Few basic definitions. We will define a quantization level. What does that mean? Then we will define a word called quantile, also known as step size, also known as quantile interval. Then we will define quantization error, which is the rounding off error resulting from that process called quantization. We'll try to quantify this error into a term called quantization noise, which we are adding to the signal due to the quantization process. So a few basic things like this. If you take a signal, let's say some analog signal, assume that its maximum value is xp, peak, p for the peak value, right? Minimum is say minus xp on the other side. Then individual steps here, you are going to divide this into multiple steps now. Right? Each step is delta V, and delta V is also known as Q, quantile, or quantile interval. These are the other names, so that's delta V. So you are going to divide into multiple delta V's. This will be 2 delta V, 3 delta V, likewise. Delta V steps. Assume that total you have, now this kind of a level, we call a quantization level. So this is the first quantization level, delta V. 2 delta V is the second quantization level. So the word quantization level means a particular delta V value. Right? Assume that we have capital L number of quantization levels defined here. Approximately, your step size will be, or quantile will be, 2xp upon L. 2xp range, you are dividing into L quantization levels. Right? Uniform or uniform. So creating another error, plus error this time. If this is delta V, maximum error possible is delta V by 2, which occurs right in the middle position here. So your error, quantization error, if you want to minimize the quantization error. Later, each of these levels we can assign to a binary number for transmission. That part we call coding. Coding we will look at separately. At the moment, we are concentrating on these approximations called quantization. Now, for example, this is a quantized signal. The staircase kind of a look. This staircase depict quantized signal. The sine kind of a shape is the analog signal. So you can see there are approximations happening. And these approximations, is can go up to delta V by 2 in a place like this, maximum error, delta V by 2. In a place like this, less error, lower than delta V by 2. So if you take for every sample, there will be approximating error called quantization error. This is an example where the sample numbers are plotted this way. Sample number 0, 1, 2, 3, likewise. For sample number 1, this much of error, minus some value. Sample number 2, this much, likewise. You can plot quantization error per sample that way, right? What does this mean? Maximum will be 0.5 times delta V by 2. 0.5 means delta V by 2. This is minus delta V by 2. And any other value possible here. Delta V could have infinite possibility, infinite number. We will assume that each of these error values are equally possible, right? So probability for an error like this to happen is same as probability for an error like this to happen. Uniform probability. So if I plot the probability density function, which plots the probability of Q, this will be minus delta V by 2 error. This will be plus delta V by 2 error. Since all voltage error values are equally probable, I am drawing a flat line here, equal probability, all of them. But all should be 1. Therefore, how much should be this height? This height should be 1 over delta V, isn't it? So probability density function will be flat at a value of 1 over V. So now we know that there is 1 over delta V probability for an error value to occur. Using that, we can find quantization, the power of the quantization noise. Right? If you know the quantization error PQ, suppose you take the Q value, which is the quantization error voltage, and you square it, you get the power. Multiply that by the probability for that occurrence to happen, and then you can integrate the errors from minus delta V by 2 to plus delta V by 2. You can get quantization noise, which is the power of the quantization noise, which you have created due to these approximations. Okay, so let us do that. This is what I already mentioned, right? So I will call it x hat t, which is the original xt plus the quantization error you created. And the power of all these q's will be power of individual quantization error, which is q squared, multiplied by the probability that error to occur, pq, and then integrate it, because this is a random signal now with a uniform probability distribution. You can derive the power of that signal, power of this random signal, using this formula. PQ is already known, which is 1 over delta V, we proved. Substitute 1 over delta V for this. Integrate Q squared, Q cube upon 3, substitute. substitute the limits, you will get the quantization noise power as delta V squared by 12. But delta V, we already know it is 2xp divided by L. Substitute that to this equation, then you can get that in terms of L. Let's call it NQ. NQ is noise of the quantization. Sorry, this is quantization noise, NQ, which is peak value of your signal xp squared divided by 3 times quantization level squared. Signal power, because signal is xt, power of the signal is x squared t. Right? Power of the quantization noise we already know. Therefore, we can find signal to quantization noise ratio we have created by this equation. So we have done an approximation and we have made an error in our signal due to those approximations, but we have now quantized how much degradation of the quality we have created because of that. We can account it by this signal to quantization noise ratio. If this is high, then we know that our quantization is yielding too much of noise. So we need to minimize S over NQ and keep it within limits. Right? That's the use of this equation, which I will highlight next time, how to make use of this and how to interpret these parameters practically and see how we can decide the number of quantization levels in a given application. Right? Okay, I think that's what the time permits today. I will stop here, and next Wednesday we will try to finish this quantization and coding both, right? And that will be my last lecture also because I'm on leave, sabbatical leave. So by next week I will complete my part. From my part, give an evaluation also, which I will announce next time, but we'll keep a time gap sufficiently. Anyway, you can look at the analog modulation section, which we can later agree upon a date and have a small assessment on that, right? And I'll provide a tutorial also for you. Give a tutorial also to practice, right? No, you will not have a quiz next week. One of you asking. It's not next week. I just announced that there will be an evaluation. So next week we can agree upon a time. It may be, if you need one more week, let's have one more week, right? Okay. Not immediate week. Hopefully one more week gap will be enough, isn't it? So not next week, week after next, I will hand over that quiz to Dr. Samiru, right? Okay, but I think you can start preparing. Do a small revision on analog modulation part now, right? Any questions you come across, please bring forth in the next lecture so I can elaborate. Okay. Right. Thank you very much for attending. Have a nice day. We'll stop there.